Good morning. We promised that we are going to calculate the thrust force in forward flight using the blade element theory and the Glauert theory. We need this for the simulation model that we are going to build. If you recall the equations of motion in a longitudinal plane. How to determine this thrust force? Now first you have again to remember that we can work with more system of references. The tip-off plane, the shaft plane, the non-feathering plane, or the control plane. I'm going to derive you first the thrust force in the blade element theory. This demonstration will consider the control plane as the plane of reference for the rotor. If you remember, the thrust force was the decomposition of the lift and the drag force on every blade element, and it could be approximated with the lift on the blade element. And you can also recall the expression of the lift on the blade element. It follows that if we know the velocity on that point of the blade and if we know the angle of attack, we can perform the integral. Now, what is the angle of attack and the velocity on the blade element? You recall that in forward flight there is a tangential component and the perpendicular component of the velocity. The tangential component is containing the omega r, the tip speed, and its component is containing the component of the tangential component of the velocity v cosine of alpha d at a certain azimuth. And also that the perpendicular component of the velocity is involving the induced velocity and the component coming perpendicular to the plane. Therefore, the velocity of the blade is omega r plus some v cosine alpha c sinus mc, and the angle of attack is pitch minus inflow angle, so equals with theta minus all this tangent of this angle. Substituting 8 and 9 into the expression of the lift, it results into an integral from dr. Now, if we are integrating from 0 to r and then on the blade azimuth 0 to 2 pi and we multiply with the number of blades and divide by 2 pi, and if we are making the notation of the thrust coefficient as the thrust divided by a coefficient rho omega r squared pr squared, if we are performing the integral and we are considering the non-dimensional component of the velocities perpendicular to the control plane, lambda c and lambda e, performing the integral, we will obtain the final formula which you see in many helicopter books. The CT blade element equals CL alpha sigma solidity divided by 4 multiplied 2 over 3 theta 0 collective pitch multiplied 1 plus 3 over 2 advance ratio squared minus lambda e plus lambda c. This formula you will need it in the simulation model. However, the thrust force can be also calculated using the Glauert theory. This time we will consider the tip-off plane as the plane of reference for the rotor. In a tip-off plane, you remember that the conservation of the angular momentum gave us that the thrust equals with the mass flow rate multiplied by twice induced velocity, the velocity of the wake down in the helicopter motion. But you remember also that the mass flow rate could be extended according to Glauert in according to rho PR square VR. Here is where you see that we need it now to apply to consider the tip-off plane as a plane where we can calculate this thrust force. Therefore, substituting 18 and 17 into 17, it gives us the thrust expression. Now, we just have to know what is the disk plane. Well, using the disk plane angle, it is actually the angle of attack with respect to the control plane minus A1, the longitudinal disk tilt. So usually integrating this non-dimensionalizing this thrust force, we obtained the CT as expressed in a Glauert. This formula we will also need it in the simulation model, as we are going to find out the induced velocity in an algorithm involving the blade element thrust force calculation and the Glauert um, thrust force calculation. This ends this calculation of the thrust forces for forward flight.